If matter looks solid and still, why does modern physics reveal a universe in constant motion?
Well, that is exactly the paradox we're dealing with today. We naturally trust our senses, right?
Of course.
But, our senses are actually lying to us.
Yeah, like I'm looking at the desk in front of me right now. I knock on the wood and it pushes back.
Mm-hmm.
It feels completely anchored, completely stable. But everything I've been reading suggests that this stillness is just, it's entirely a macroscopic illusion.
It really is.
Like if I had microscopic vision, I wouldn't see a solid block of wood. I'd see this incessant, frenetic activity.
Yeah, you'd see a relentless storm, really.
Right. We're talking about molecular collisions, vibrating electromagnetic fields, atomic chaos. The deeper you look into the fabric of reality, the more restless it actually gets.
Exactly. The illusion of stability is incredibly convincing. But to truly understand reality, we have to kind of, peel back those layers.
And how do we even begin to do that?
Well, think of it as a descent into the microscopic. We'll start with the things we can intuitively grasp, how gases exert pressure, how heat is just a microscopic motion, and how probability rules the molecular world.
Okay, that makes sense.
But then once we understand particles, we have to look at the empty space between them, which pulls us into classical waves, the weird dual nature of light and relativity.
Wow. Okay, so we're going all the way down.
We have to. Eventually, that journey forces us to crack open the atom itself. We land in the bizarre mechanics of the quantum realm before finally reaching the absolute core.
The nucleus.
Right. Nuclear forces, cosmic rays, and modern particle physics. And I should say, we can't do all of that without eventually confronting what this immense knowledge means for us as a society.
I love that framework. But before we take that descent, I just want to add a quick note for our listeners.
Sure.
This deep dive is an independent Cosmora HQ book overview. It is not an official or complete audiobook of Max Born's classic work, The Restless Universe.
Yeah, it's our own discussion of it.
Exactly. So we highly encourage you to seek lawful access to the canonical book for the full original experience.
It's a remarkable piece of scientific history, really, and understanding its progression kind of, well, it changes how you view the physical world.
Let's start with that first layer you mentioned then, the things we can feel but can't see.
Okay.
Like wind blowing against your face or the resistance you feel when you squeeze a blown-up balloon.
Right.
I'm interacting with air, which is mostly empty space populated by invisible bits of matter. How does empty space push back with such forceful, stable pressure?
So the mechanism there is something called kinetic theory. When you press on that balloon, you might imagine you're compressing a static, sponge-like substance.
Yeah, that's kind of how it feels.
But in reality, you're experiencing this massive statistical effect. Inside that balloon, billions upon billions of gas molecules are just hurtling around at high speeds.
Like a swarm of bees.
Yeah. They're constantly slamming into the inner rubber wall and bouncing off. Every single invisible collision transfers a tiny, discrete bit of momentum.
Okay, let me see if I'm visualizing this correctly. I'm picturing a chaotic, enclosed room filled with thousands of tiny, indestructible billiard balls.
Okay.
And they're constantly ricocheting off each other and the walls. The sheer volume of those impacts happening every millisecond creates the illusion of a steady, constant outward push.
Exactly. Well, up to a point.
Right.
Yeah, that analogy helps us grasp the concept of pressure, but it has a pretty crucial limitation. Molecules are not miniature, hard billiard balls.
They aren't.
No, they aren't solid little spheres. They have complex internal structures. They vibrate, they rotate, and they interact with each other through complex electromagnetic fields long before their physical centers ever touch.
Oh, wow. Okay, so they're a lot messier than billiard balls.
Much messier. But if we zoom out and look at the statistical averages of all that movement, the kinetic model predicts pressure beautifully.
Okay, so speaking of moving around, I want to ask about temperature in this context because this always trips me up. Go for it. If heat is just molecular motion, does a single molecule have a temperature? Like, if I somehow catch one of those speeding molecules, is it hot?
Yeah, that's a fundamental trap people fall into. A single molecule does not have a temperature.
Wait, really?
Really.
Right.
It only has a specific velocity and kinetic energy at a given moment. Temperature is a macroscopic property.
Oh, I see.
It characterizes a statistical distribution in a many-particle system. In that balloon, some molecules are moving sluggishly, others are zipping around at supersonic speeds.
Right.
The overall distribution of those varying energies is what gives us the measurement we call temperature.
So historically, when scientists thought heat was a literal fluid-like, I think they call it caloric,
Yes, caloric fluid.
yeah, flowing from a hot object into a cold one, they were completely misinterpreting the
They
mechanism.
were.
Heat isn't a fluid. It's just the transfer of microscopic kinetic energy through collisions. A fast, hot molecule smacks into a slow, cold one and speeds it up.
Precisely. And scientists didn't just have to take the math's word for it. They found observed evidence of this chaotic molecular dance.
What kind of evidence?
The most famous example is Brownian motion. Back in the 1800s, a botanist named Robert Brown was looking at tiny pollen grains suspended in water under a microscope.
Okay.
And he noticed they didn't just sit there. They jittered and jerked around randomly in these zigzag paths.
Were they alive? Or did he think they were?
That was a theory. But no, it wasn't alive. It was eventually proven mathematically by Einstein and confirmed by observation that this visible irregular motion is caused by invisible water molecules.
Oh, just constantly agitating and slamming into the pollen grain.
Exactly, from all sides. Because the impacts are random, sometimes slightly more molecules hit the left side than the right, shoving the pollen grain around.
That is incredible. We could actually watch the invisible world bullying the visible one.
Yeah, that's a great way to put it.
But here is where I hit a wall. Structurally.
Okay.
If matter is just this vast, vibrating swarm of particles constantly smacking into each other, how does energy travel across a room where there are no particles to carry it?
What do you mean?
Like, if the space between me and a light bulb is a vacuum, how does the energy from the bulb reach my eyes?
Okay. To answer that, we have to stop thinking about physical particles colliding and start thinking about the propagation of energy through fields. We have to enter the realm of classical waves.
Okay, with sound, I get it. I speak, my vocal cords vibrate the air molecules in my throat, those smack into the next molecules, and a pressure wave travels to your ear.
Right.
But light, or electricity, or magnetism, they clearly push and pull things across empty space.
Yeah, James Clerk Maxwell gave us the mechanism for this. He realized that moving electric charges create magnetic effects. And conversely, a changing magnetic field induces an electric current.
So they feed into each other.
Exactly. He unified these phenomena into a single theoretical framework, showing that electricity, magnetism, and light are all part of the exact same phenomenon.
Propagating electromagnetic waves.
Right. An oscillating electric field creates an oscillating magnetic field, which creates an electric field propagating outward forever.
Okay, let me try another analogy here.
No.
I picture an electromagnetic field like the surface of a pond.
Okay.
You turn on a light bulb, which is like dropping a pebble into the water.
Yeah.
Ripples of energy travel outward through this invisible mechanical fluid that just fills the entire universe.
It's a compelling visual for understanding frequency and wavelength, but you're falling into the same trap 19th century physicists fell into.
Uh-oh. What did I do?
They assumed there had to be an invisible fluid. They called it the ether filling all of space for the waves to ripple through.
Right, the ether.
Yeah. The fundamental limitation here is that electromagnetic fields do not require a physical medium. Unlike water waves that need water, or sound waves that need air, electromagnetic fields can travel through a perfect vacuum.
So there's no fluid.
No fluid. The fields themselves are real, physical entities that oscillate.
Which is a massive conceptual leap. But it gets so much weirder when we look at the experiments trying to prove what light actually is.
Oh, absolutely. The historical debate over whether light was a wave or a stream of particles was fierce, primarily because the evidence seemed completely contradictory.
Right.
First, you have the famous double-slit experiment. You shine a light through two narrow, parallel slits and project it onto a screen behind them. If light were just particles, like sand, you'd expect two bright bands on the screen.
But that isn't what happens. You get a whole series of alternating bright and dark bands spreading out across the screen.
Yeah, an interference pattern.
Which is the hallmark of a wave, right?
Exactly. When the crests of two waves meet, they amplify each other, creating the bright bands. When a crest meets a trough, they cancel each other out, creating the dark bands. That observed pattern firmly anchored light as a continuous wave.
Wait, I'm stuck here. If the double slit experiment proved light as a continuous wave, what about the photoelectric effect? Because my understanding is that this completely broke the wave model.
It did.
Because if light is a continuous wave beating against a piece of metal, sort of like ocean waves beating against a cliff, shouldn't a really bright, intense light eventually build up enough force to knock an electron loose from the metal?
That is exactly what classical physicists assumed. They thought if you cranked up the brightness, eventually the energy would accumulate and pop an electron off.
Ooh, it didn't.
No, the observation completely defied the theory. A hyper-intense beam of red light could shine on a metal all day and never eject a single electron.
Wow.
But a very dim beam of ultraviolet light would knock electrons off instantly. Why? Because the photoelectric effect shockingly revealed that light also behaves in a quantized manner.
Meaning it interacts in discrete packets.
Yes, the energy isn't continuous. It's delivered in indivisible chunks quanta, which we now call photons.
Okay, so it's tied to color.
The energy of a single photon is tied strictly to its frequency, its color. A red photon simply doesn't carry enough energy to knock an electron loose, no matter how many red photons hit the metal.
But a single ultraviolet photon does.
It has enough energy to do the job instantly. This proved light requires quantized energy exchange.
That actually reminds me of a common misconception about electricity.
Oh, yeah?
Yeah, once we discovered electrons, these tiny, negatively charged constituents of matter using vacuum tubes, people started reducing electricity to a classical cartoon.
Oh, like water flowing through a pipe.
Exactly. But electric fields are fundamentally different from mechanical fluids, just like pressure isn't a substance stored inside a gas.
Right. The deeper we go, the more our microscopic analogies fail us. We constantly have to upgrade our mental models.
So if light is interacting with these newly discovered electrons in such highly specific, quantized ways, I imagine physicists realized they could use light to figure out what was happening inside the atom itself.
They absolutely did, primarily through spectral lines.
What are those?
Well, when you heat up a specific gas, like hydrogen, it doesn't glow with a continuous rainbow of light. It emits very specific, distinct colors, sharp lines of specific wavelengths.
Oh, like a barcode.
Exactly like a barcode. Those spectral lines act as unique, unforgeable atomic fingerprints for every element in the universe.
But to figure out why hydrogen emits those specific colors, we had to probe the atom. And you can't just crack an atom open with a hammer.
No, you definitely can't.
We had to use high-energy particles to shoot at it. And my understanding is to comprehend high-energy physics, we had to completely revise our understanding of reality, bringing in special relativity.
They did.
Why did the speed of light suddenly dictate how we study matter?
Because it turned out the speed of light in a vacuum is absolutely constant for all observers, no matter how fast they're moving.
Right.
To keep that speed mathematically constant, Einstein showed that our theoretical assumptions about space and time had to be wrong. Space and time are not absolute rigid stages.
So they can bend.
At high velocities, time actually dilates, it slows down, and lengths physically contract. You cannot calculate the momentum or energy of particles moving near light speed without relativity.
And relativity also gives us the most famous equation in history, EMC squared.
It does.
I really want to correct a major interpretive misconception here because pop culture has totally distorted this. People often think the equation means that if you smash atoms together, their mass simply vanishes. Like, poof, a magic trick, and turns into pure energy.
Yeah, that language is highly misleading. Mass does not disappear into nothingness.
Thank you.
We must carefully distinguish between an object's invariant mass, which is the intrinsic property of the matter itself, and a system's total energy.
Okay, so what does EMC squared actually tell us then?
It tells us about mass-energy equivalence. A body's mass is a measure of its energy content. In nuclear reactions, a tiny fraction of the binding energy holding the system together is what gets released.
Ah, I see. So, armed with this high-energy physics, we finally get to Ernest Rutherford's gold foil experiment. This is where the visualization is stunning to me.
It's a great one.
They fired heavy, incredibly fast alpha particles at a sheet of gold foil that was just a few atoms thick.
Yeah, and based on the models of the time, they expected the heavy alpha particles to punch right through the atoms, maybe deflecting by a fraction of a degree.
Because they thought it was solid.
They thought the atom was a soft, somewhat uniform smear of positive charge with negative electrons embedded in it.
Like a plum pudding.
Exactly.
But the observed result defied all logic. Most of the particles went straight through without hitting anything, but a very rare few bounced at massive angles. Some even ricocheted straight back at the source.
Yeah, Rutherford famously said it was like firing a 15-inch naval artillery shell at a piece of tissue paper and having it bounce back and hit you.
That is so crazy.
It was a monumental discovery. It proved that the atom isn't a solid mass at all. It's overwhelmingly empty space, surrounding an unimaginably tiny, unimaginably dense, positively charged core,
The nucleus.
the nucleus.
This is where my mind immediately jumps to the Bohr model.
I bet.
If there's a massive core in the center and electrons on the outside, the atom must be a miniature solar system. The dense nucleus is the sun, and the electrons are the planets orbiting around it in perfect fixed paths.
We have to firmly reject that classical picture.
What, really?
Yes. The planetary model was an important historical stepping stone for Niels Bohr to explain those spectral lines, but it's physically inaccurate. Electrons absolutely do not follow fixed, predictable paths around a nucleus.
Oh.
And furthermore, when we say the atom is mostly empty space, we don't mean classical nothingness. That volume is richly defined by interacting quantum fields and bound state structures.
Okay, so if they aren't orbiting like planets, how do they stay around the nucleus without crashing into it? What are they actually doing?
Well, this brings us to the true quantum casino, wave mechanics.
The idea that matter itself behaves like a wave.
Exactly. Louis de Broglie introduced the theoretical concept of matter waves. He proposed that just as light has particle properties, matter, specifically electrons, has wave properties.
That sounds like pure math.
It wasn't just mathematical speculation, though. It was confirmed by the observation of electron diffraction.
Wait, you can diffract an electron?
Yeah. When scientists shot a beam of electrons through the precise repeating grid of a crystal, they didn't just scatter like bullets. They created a complex interference pattern on the detector behind it.
Wow.
That undeniably connected a physical particle's momentum with a wavelength.
See, I'm struggling to visualize an electron wave. Are these waves physically sloshing back and forth in three-dimensional space inside the atom? Like water trapped in a bowl?
No, and you've hit on the exact limitation of our microscopic vocabulary again. Erwin Schrödinger developed the wave mechanics to describe this, but a quantum wave function is not a physical wave in 3D space.
It's not.
No, it is a complex mathematical tool that encodes all the possible states of the system.
Which is where Max Born's genius completely reshaped physics. He provided the statistical interpretation of what Schrödinger's math actually meant in the real world.
He did. Born realized that if you take the squared magnitude of this quantum amplitude, it gives you a probability density.
Okay, unpack that for me.
It doesn't tell you exactly where the electron is. It tells you the structured probability of where you will measure it to be if you look.
Which leads to another massive public misconception.
Oh, for sure.
Because when people hear quantum mechanics is based on probability, they assume it means everything is purely random chaos. That an electron could just teleport anywhere in the universe because anything is possible.
That completely misunderstands the math. The probabilities are intensely structured. An electron bound to a hydrogen atom has distinct geometric regions, orbitals, where it's highly probable to be found, and nodes where the probability is absolute zero.
But this does mean we can never know everything about the particle at once.
Correct. Heisenberg's uncertainty principle and Bohr's complementarity reveal the fundamental limits of nature. It's not that our measuring equipment is defective.
Right.
It's that the universe itself, at that scale, simply does not possess simultaneously definite values for paired properties like position and momentum. The more precisely you pin down where an electron is, the less defined its momentum becomes.
And out of that blurry uncertainty comes the rigid order of our entire world. Because these quantum rules dictate how electrons arrange themselves, giving us quantum numbers, spin, and Wolfgang Pauli's exclusion principle.
Pauli's exclusion principle is the invisible architecture of reality, really. It states that identical fermions particles like electrons cannot occupy the exact same quantum state simultaneously.
So if one electron is occupying a specific energy state around the nucleus and another identical electron tries to squeeze into that exact same state, the universe literally pushes back.
Exactly. They cannot stack infinitely on top of each other. Once a quantum state is full, the next electron has to go into a higher energy shell, further from the nucleus. This creates the distinct electron shells.
And the way atoms share, trade, or stubbornly hold on to those outermost shell electrons, that is the entire periodic table.
It is.
That gives us chemistry, biology, the structural integrity of metals, everything.
But all of that chemistry requires incredibly low amounts of energy compared to what's happening at the center of the atom. We've mapped the electron shells, now we have to breach the core.
The nucleus. This is where the scale of energy gets terrifying and where we encounter the invisible radiation passing through our bodies right now.
Yeah, at the nuclear scale, we leave chemistry behind entirely. We're dealing with isotopes, X-rays, radioactivity, and nuclear binding energy.
It's a whole different beast.
It really is. Inside the nucleus, you have positively charged protons packed impossibly tight. Electromagnetically, they should violently repel each other and blow the atom apart.
Because, like, charges repel, but they don't. Because of the strong nuclear force.
Yes, the strong force operates over incredibly short distances, but it's powerful enough to overpower the electrostatic repulsion binding protons and neutrons together.
But that balance isn't always stable. Some isotopes decay. When I try to explain radioactive decay, I often describe it like a ticking time bomb inside an unstable atom, counting down to a specific, predetermined moment when it will spontaneously rupture.
That analogy actually breaks down at the fundamental level.
It does.
Yeah. Radioactive decay is entirely statistically predictable for large ensembles, vast groups of atoms. We know exactly how long a half-life is for a block of uranium.
Okay.
But the individual decay time of a single specific nucleus is entirely unfixed and unpredictable. You cannot look at one atom and know when it will pop. It's the ultimate expression of quantum probability.
Wow, okay. We really need to clarify the distinct boundaries here because pop culture lumps all this together. People think ordinary chemical reactions, radioactivity, fission, and fusion are all just varying degrees of atomic energy.
Oh, they involve entirely different mechanisms and energy scales.
Need you break that down?
Sure, a chemical reaction like burning wood is just the swapping of outer electrons. The energy released is tiny. Radioactivity, on the other hand, is the spontaneous, uncontrolled decay of an unstable nucleus.
Okay, and fission.
Nuclear fission is actively splitting a heavy, stable nucleus apart, which releases millions of times more energy than a chemical reaction and can trigger a cascading chain reaction.
All right, and fusion.
Fusion is the process of forcing light nuclei together, which is what powers the sun, so they are fundamentally distinct.
And physicists in Max Born's era didn't figure all of this out just by smashing things in a lab. They looked up. The universe provided its own natural particle accelerators.
Cosmic rays.
Right.
These are incredibly energetic particles streaming across the galaxy, constantly slamming into our upper atmosphere. By detecting and studying these observed high-energy collisions, physicists discovered subatomic particles like positrons and pions that were completely inaccessible to the laboratory equipment they had at the time.
Which brings up a critical historical context. Max Born wrote the Restless universe in a specific era. Physics didn't stop there.
No, we really must separate the historical model-dependent physics of Born's time from the modern update. Born knew about protons and neutrons. We now know those are not fundamental particles.
They're made of smaller things.
Right. They're made of even smaller entities called quarks, permanently bound together by the exchange of particles called gluons, which carry the strong force.
And we didn't just find quarks.
We discovered the full family of leptons, including the elusive neutrinos that pass through the Earth by the trillions every second without hitting anything.
That's wild.
We developed the framework of quantum fields and gauge interactions, where forces are mediated by the exchange of fundamental particles. We synthesized all of this into the standard model of particle physics.
It is genuinely overwhelming to realize how deep the Restless universe goes. But as Born points out at the end of his book, pulling back these layers didn't just result in a neat set of equations on a chalkboard. It handed humanity unprecedented existential power.
Yeah, the whole book's synthesis really lands on this tension. The universe is dynamic and vibrating across every conceivable scale: molecular, atomic, nuclear, cosmic.
Right.
Our physical knowledge of these mechanisms inevitably transforms civilization. Understanding nuclear binding energy wasn't just a triumph of human curiosity. It led directly to the creation of the atomic bomb, nuclear reactors, and geopolitical paradigms that define our modern world.
And looking at that historical and social appendix, we have to reflect impartially on the role of science. The profound takeaway is that science provides the mathematical framework to understand reality. It hands us the mechanisms to harness astronomical amounts of energy.
Yes, but the equations themselves are morally neutral.
Exactly. They cannot tell us how scientific power should be governed by society.
Science dictates the how. It dictates the boundaries of what is physically possible. It does not and cannot dictate the odd.
Right.
The responsibility for how we use our mapping of the restless universe falls entirely on human ethics, judgment, and social organization.
It fundamentally changes how you walk through the world. The ground beneath our feet isn't solid, the air isn't empty. We're just riding on the surface of a boiling quantum sea. If the universe never truly rests, what does stability really mean?